Okay, looking at what we have regarding first order non-homogeneous equations examples. Let's say that we're looking at trying to solve for y of x, first of all, whereupon we have y prime is equal to x times e to the x. And if we look at this one first of all, okay, now a non-homogeneous equation is going to be comprised of two parts here. We're going to have what is going to be the sum of what will be referred to as the complementary solution, and we can just call that y sub c of x. And then we have a particular solution, which we can refer to as y sub p of x. And the complementary solution would be if you had the equation to be homogeneous, that is, if you had it set equal to 0. Okay, so if we were to go ahead and look at if we had y prime is equal to 0. Well, if I were to put this in the characteristic root equation format, okay, so you have like r is equal to 0, and we have only one root, okay, where we would have r sub 1 is equal to 0, and we would have in effect that y is equal to a constant c sub 1. Okay, and so that is going to be the complementary solution. So we have y sub c of x is equal to a constant. Now for what we have, instead of having y prime equal to 0, we have it equal to x times e to the x. And if we look at the variable factors, okay, first of all we have x, and just using as a bit of a guideline, okay, we have like you have like the constant value functions. Okay, so a constant value had the family of functions to consist of a constant. For raised powers of x, you have like x to the n minus 1, all the way down to where you have a constant. And what we're looking at in this family is like you're looking at a finite family of derivatives. Okay, so starting out with the original term, so we have with x. Okay, so you have x, and the derivative of x is going to go to a constant. And we have with our other factor in x, we have the natural logarithmic base e, which is raised to the x. And guess what? You have e to the x, and any derivative of this is just going to be e to the x. And looking at setting things up and solving for this particular non-homogeneous equation, so you have for x times e to the x, if you look at taking the family of terms and derivatives that we have for x as well as e to the x, okay, so we have from x, I have x and c. From e to the x, I have just e to the x. And if I look at distributing, so to speak, so I have like taking the product of x and e to the x, and we have c times, or constant times e to the x, and just putting everything in diminutive terms. Okay, so we have x, e to the x, and with constant times e to the x, you're just looking at a direct multiple of e to the x. Okay, now for this equation, we had the complementary to be a constant. Now for the particular solution setup, we have in general terms, now we're going to have y sub p is going to be equal to a, and we can say that from combining the family of terms and derivatives from x times e to the x. So I can say that I have a times x times e to the x, and with e to the x I can say that I have plus b times e to the x. And again, we are looking at a first order derivative in the equation. So if I were to take a first order derivative of the particular for ax e to the x, we have, with the product rule, we have a times x times the derivative of e to the x, so that will go to ax e to the x. And taking e to the x times the derivative of ax, well, guess what? That is going to be a e to the x. And for be to the x, we're just going to have another be to the x. And setting the particular solution derivative equal to xe to the x. So you have from the original equation. So if I set y sub p prime equal to x times e to the x, but we have this simultaneous existence of what we have for y sub p prime. So I can set these expressions equal to each other. And I'll just copy what I have here. And if you notice, on both sides of the equation, okay, I have xe to the x terms. But if you notice, on the left I have ae to the x plus be to the x, but I do not have a standalone e to the x term. So I'll just say that I have plus 0 times e to the x. And if I look at mapping together what we have here, so you have ax e to the x on the left and xe to the x on the right, and I can just set these terms equal to each other. So you have ax e to the x is equal to x times e to the x, and from this, if I divide both sides by xe to the x, I will have that a is equal to 1. Now for the e to the x terms, there's I have a e to the x plus be to the x, and to the right I have 0. So in effect I have a e to the x plus b times e to the x is equal to 0 times e to the x, and we can just divide out the e to the x and just say that we have a plus b is equal to 0. Well, guess what? We already have that a is at 1. And we have 1 plus b is equal to 0, from which we are going to have that b is equal to -1. So going back to what we have for the particular solution, notice that we had in the original setup, you had y sub p is equal to ax e to the x plus be to the x, and with a at 1 and b at -1, we have for y sub p of x then we have 1 xe to the x, or just plain xe to the x, and plus be to the x, and that's going to be a -1, or just the negative of e to the x. And looking at what we have all together, again, you have y of x is equal to y sub c of x plus y sub p of x, and y sub c of x, that is equal to the constant. So all in all, you're going to have that y of x is equal to your y sub p of x whereupon we have x times e to the x minus e to the x, and we have with the constant from the complementary, and this is going to be the outcome for what we have in the first non-homogeneous equation. Okay, now for the second equation, we have y prime is equal to 5. So we have another non-homogeneous equation. Now just going ahead and taking on the complementary part of this. And once again, we have for the complementary solution, that is just going to be a constant. We'll just call this c sub 1. And guess what? For the terms of which we have y prime set equal, okay, well this is a constant. And what's going to happen here is that for the number 5, well guess what? You got the number 5, and 5 is already a constant. Now looking at what we have here, notice we have what is regarded as a duplication. And anytime you have a duplication, what you're going to do is that you're going to multiply what's in the family of functions by x. So if multiply by x, so you have like a constant times x, and just putting in, once again, diminutive terms, this goes to x. And we have only one term inside this particular family, and so we can have as a general particular solution setup, we have that y sub p of x is equal to a times x. Alright, so we have with y sub p of x equal to a times x. If I take the first order derivative, I'm going to have y sub p prime of x is going to be equal to a. And notice I have y prime is equal to 5. So if I were to set y sub p prime equal to 5, and guess what? On the one end, I have y sub p prime of x is equal to a, and y sub p prime of x is equal to 5. And guess what? I'm going to have that a is equal to 5. Okay. And with the value of a determined, and looking at what we have with the initial setup for y sub p, okay, so we have a is at 5, y sub p of x is equal to a times x, and it's going to turn out that for what we have in the solution for the particular part of y of x, we have y sub p of x is equal to 5x. So for what we are going to have altogether, okay, we have y of x, again, is equal to the sum of what we have between the complementary and the particular solutions. And so that's going to be like 5x plus c sub 1. And that is going to be the entire solution of what we have with this first order non-homogeneous differential equation.